Welcome to Part 3, the Science and Engineering video on the Crosswind anti-COVID solution. We know that transmission of respiratory diseases through the air fundamentally depends on the separation distance and the exposure time between the infected and healthy person. The shorter the distance or the longer the exposure, the greater is the risk of infection. So theoretically, if we can increase that distance to infinity or exposure time to zero, there will be no transmission and no pandemic, of course, but also no society either. Thus, to keep society intact, to at least some degree during a pandemic, we have adopted measures like minimum distancing and masking, but those are proving insufficient. In indoor spaces, the 2-meter distancing rule is indeed effective against large microdroplets, but it is ineffective against aerosol transmission and is especially ineffective against the highly infectious variants. Masks do help, of course, but as we will see coming up, they don't solve the problem entirely. Here, I demonstrate how technology can help. Here is a paper from Los Alamos Laboratory that pegs the basic reproductive number R0 at 5.7 for SARS-2. At the time of this recording, there are new very contagious variants originally detected in the UK, South Africa, and Brazil that could drive the R0 value beyond 8, underscoring the airborne nature of this virus requiring even stronger measures for those of us who are most vulnerable. This pertinent study characterized the aerosol emitted by masks. In the first part of the study, this group looked at particle size distributions. Care attendants wear surgical masks when breathing and talking in close proximity to their residents, which is the combination we are interested in solving. The group found that emitted aerosol particles range from 0.3 microns to 5 microns, where the majority of individual particles were smaller than 1.5 microns. Now here is something interesting that I noticed in their data. The low frequency of those particles larger than 1.5 microns appears to be insignificant, but it is not. We will get to that momentarily. Let us first have a quick look at particle settling time. From many studies done to date, we can safely say that surgical masks are effective at removing microdroplets larger than 10 microns. Relevant to the particles on the left, an aerosol is a mixture of gas and tiny particles in which the particles are small enough to stay suspended, not dropping to the ground. The mixture of air and particles leaked through a surgical mask is an aerosol. If those particles contain pathogens like SARS-2 virions, then those particles are called an airborne contagion because of their persistence in the air and ability to cause either immediate infection at short distances or latent infection at longer distances, even after an infected person has left the room. I have concluded that it is this mask-emitted aerosol that presently appears to be responsible, certainly at close range that is already violating the standard 2-meter distancing rule, for the majority of infections in long-term care centers. In this slide, the same group measured the difference in the quantity of aerosol particles emitted through a surgical mask compared to no mask for the normal activities of breathing and talking. They found that for breathing, a surgical mask provided a 5-fold reduction of particles. For talking, the reduction was 15 times. So this study showed that under average expiratory activity in a residence, for every 10 aerosol particles trapped by a mask, 1 escapes. Therefore, it is this one nasty particle which is the dominant culprit in residence outbreaks, coincidental with the fact that residents do not wear masks. So it is this one we want to get rid of. We saw in the previous video how deflection can protect you against initial aerosol clouds emitted by a masked infected worker breathing and talking in close interactions. I also proposed that an air filter could work to reduce latent aerosol infection after the worker has left the room. So you might be asking, how well does this idea really work? Let's answer that question by exploring the performance of the filter stack we chose for this solution in its effort to tackle infectious aerosol reduction. Here we see again the distribution of aerosol particles. Recall this seemingly unimportant part of the graph? It is already common knowledge from the literature that probability of infection and its severity is directly proportional to the inhaled viral load. So how could we get that hidden data from this graph? The key observation to note is that not only is the viral load related to the frequency, but the load is also proportional to the spherical volume, the cube of the radius of each particle. So if we crunch the equation, we get this interesting violet curve. Finally, the total airborne viral load is the area under the violet curve. Let us see what this really means. Due to the logarithmic scale of the diameter axis, understanding its significance becomes clearer when we stretch the graph horizontally. Mapping the large particle portion like this, we see that the total viral load consists of 20% small particles and 80% large particles. Therefore, it is the large aerosolized particles that dominate infection probability despite their low frequency. Now let's see how this result plays into our choice of our three filters. You can ask, why not use just one HEPA filter? It turns out that the high fiber density of a HEPA filter would completely block airflow, rendering the deflection component of the solution ineffective with a household box fan. Because the crosswind air barrier is the core part of the solution, a lower MERV choice creates a balanced trade-off for overall effectiveness of the solution. You might be wondering why 3 filters when you saw 2 in the prototype. Yes, that unit had 2 MERV 11 filters, as here. But I got a report from my mother's residents that they are concerned the outside filter is turning gray after a few weeks. So I simply improved the solution by adding a $5 MERV 8 filter that will remove environmental contaminants, helping keep the MERV 11 filters at peak efficiency for a longer time with very little impact on airflow rate. Here is a MERV 8 filter after a month and a half of indoor use on a box fan in my city with a population of 2 million compared to a new one. A discolored filter is normal and it indicates that the system is doing its job properly. Normally these filters are replaced every 3 months. Here again is the total viral load, and we are interested in how the filter stack performs over the entire aerosolized particle range up to 5 microns. Performance of an air filter is defined by its MERV characteristic for filtering differently sized particles according to a standard family of curves, shown here for a few filters. So our 3 filters are characterized by the E and C curves. We arrive at the combined effective efficiency of our filter stack by evaluating this equation, and the result is this red curve. Earlier, we defined the blue line as the boundary between the small and large particles. We note here that the small particle peak occurs around 0.65 microns on the violet curve, and mapping its range onto the red MERV graph, we see its average efficiency turns out to be 60%. For the large particles, we get an efficiency of greater than 95%. Obviously, this is becoming quite interesting. Recall that we found the viral load to be split 20% versus 80%. Therefore, combining the 2 results, small particles are filtered at 60% per pass through the filter, and the large ones at 95% per pass. We can conclude that more than 85% of the total suspended viral load range of 0.3 to 5 microns is removed from the infectious aerosol per single pass through our triple filter stack. How does that all come together in a real room? Clearly, it is not easy to visualize activity of aerosols we can't see. So we're going to ask some help from a computer animation that demonstrates the whole solution in action over time. The less severe small particle range will be symbolized as pink dots, and the more severe large particle range will be shown as red dots. Keeping these 2 colors in mind, let's watch what happens. We have 2 rooms side by side for simultaneous comparison, each with an unmasked resident who is seated. In the animation, neither room has ventilation. The left is the reference room without the crosswind solution, containing reasonably clean air at the start. Consider this resident your neighbor. Your room has the solution with the apparatus placed 2.5 meters away. Because its fan has been running for more than 7 hours at 1 meter per second in your room's volume of 150 cubic meters, the air in your room is HEPA quality. In effect, you have been breathing the cleanest air possible. Next, 2 infected workers wearing surgical masks enter both rooms at the same time while holding their breath, positioning themselves a half meter from you and your neighbor. In unison, they loudly say boo, expelling a burst of infectious particles, and we track the evolution of both aerosol clouds over the next 2 hours. Because we converted infectious particle sizes into a homogeneous viral load, 512 pink dots will represent the lighter suspended fraction at the start, and 2048 red dots will represent the heavier fraction, which we saw earlier to be 4 times as infectious as the suspended fraction. The other thing to watch for is the red word infected, whose changing font size over time will give you an idea of the relative probability of infection as aerosol distribution dynamics vary. For your neighbor in the real world, it symbolizes the existing probability of infection in long-term care in your region. It is important to understand that in reality, at your care center in general, your neighbor will not be infected every time an infectious aerosol cloud reaches her face. In your room, in contrast, the font size of infected gives you an idea of the relative reduction in the probability of infection that you will benefit from the crosswind solution with respect to your neighbor's room. The animation timeline is close to real time for the first 4 seconds and then sped up by increasingly compressed time for the next half hour until it reaches the full 2 hours. Actual duration is approximately 1 minute. If you have a spare third eye, you may glance down at the bottom to follow the clock. So now we will attempt to visualize what is normally invisible. Ready? 3, 2, 1, boo! Both clouds still have the same number of infectious particles. In less than a minute, your neighbor is already infected while you are still in the clear. If your neighbor did not get infected in reality, she continues to be in serious peril for the next 10 to 20 minutes while her cloud dissipates. Meanwhile, you are just fine and you can rest easy. In just 10 minutes, the total viral load has been diluted throughout your entire room, reducing load density dramatically compared to your neighbor. And it continues to be filtered at 85% efficiency for each pass through the filter stack. If you were to get up and walk away from your protective crosswind, your chances of getting infected would go up slightly, yes, but still remain much lower than your neighbor. Your neighbor continues to be faced with some large particles, while yours are all gone and you have only a few small particles left. At this point, I am demonstrating the best case for your neighbor. In reality, the air in her room is not entirely still. Usually there is movement even from baseboard heaters, meaning there will be more red dots than shown here and they will stay aloft in her room for a longer time. Nevertheless, her infection probability is much lower now, shown by the question mark instead of an exclamation point after the word infected. In 1 hour following the infected worker's absence, your room is safe for you to walk around anywhere. Finally, after 2 hours with the crosswind at 1 meter per second, your room is exceptionally safe. Your neighbor is still exposed to the small particles. However, if she did not get infected in the last 2 hours, it is much less likely she will get infected going forward, despite absolutely still air as in this computer model that allowed all the large particles to drop to her floor by now. Although under real conditions of even very mild turbulence, her room would still contain some red particles, whereas yours would not. Regardless of the condition of her room, you are much better off, even after 2 hours. Here you have only 2 of the small pink particles left, while your neighbor has nearly the original 512. The modeling randomizer did not place the pink dot over your head, so I moved it there by hand. I also placed a tiny infected question mark to show that in physics, in the real world, nothing is ever perfect. After 7 hours, your neighbor's room remains almost unchanged, while your last 2 pink dots are gone. And although your probability of infection is still there, it is negligible. You are now back to breathing operating room quality air only found in hospitals. For sake of completeness, I don't know if you can see it, but your infected question mark is only a few pixels in size. Let us now head towards the end of this video. We are still left with a few questions that need answers. For example, Because our filter arrangement is not HEPA, how does this solution work if there are isolated single viruses floating around in the aerosol, those infectious particles smaller than 200 nanometers? Because filtering of tiny particles is hard to measure, for this we turn to some basic air filter theory. This graph illustrates two modes of particulate removal in a filter. Removal of particles larger than a half micron is dominated by interception, where the particle hits a fiber as it travels through the filter material as a projectile. Particles smaller than 0.2 microns, such as individual viruses, are removed by diffusion, where interfiber microturbulence and electrostatic attraction dominate. The combination of both modes results in this efficiency curve, where we see that the curve begins to rise again as nanoparticles get smaller. So now, how does all that affect our filter stack? Let's have another look at our efficiency curve. Recall that our filter stack is able to remove the small particle viral load centered at 0.65 microns with an efficiency of at least 65%, which we designated with pink dots in the animation. The question now is, what is going on here in reality? We just saw that the efficiency curve tends back upwards. So let's have a look at a computer model of filters with different MERV values ranging from MERV 6 to MERV 16. We overlay our filter stack curve, and this red part is an estimation of its effective efficiency performance, which lies between a MERV 12 and a MERV 13 standard filter. So we are about halfway to answering the question. For the second part of the answer, here is what happens to a MERV 12 filter when we change airflow rate. You need to know that a MERV is given for the standard airflow rate of 500 feet per minute, which gives us the orange curve. Upon decreasing airflow, such as down to 250 feet per minute, we get the pink curve, which demonstrates an increase in efficiency in the diffusion range, where of course we could find individual viruses. It turns out that our airflow rate is a slow half meter per second through the filter stack, making it 5 times slower than the standard rate, thus improving the efficiency in the diffusion range by about 30% compared to the orange curve. So, recalling our established pink dot reference for the small particle range that gave us 65% efficiency, we note that SARS-2 viruses range from 40 nanometers to 150 nanometers, with an average size of approximately 100 nanometers. The intersection of the two occurs at 60%. So being almost identical to the small particle range, we can color it pink also. That means the computer animation is as valid for individual viruses sized down to 40 nanometers as it is for the small particle range centered at 0.65 microns, that is, in the range of around 650 nanometers. Moreover, the worst case efficiency for particles in the efficiency null, those sized between 0.2 micron and 0.4 micron, get removed at a reasonable 35% per pass. In a more robust installation, it would be more effective to install a few units on the ceiling so that worker interaction, such as repositioning and changing speeds, is eliminated. This configuration, because it is automated, means that the predicted efficacy of 99.93% has a much better chance of being achieved. Unit number 1, mounted close to the near wall, runs permanently. Unit 2, mounted at the far wall, in this example, is directed for bed operations. Unit 3, at its high-speed setting, has the very important function of providing a strong crosswind in a bathroom operation. Units 2 and 3 make use of proximity detectors to turn on only when the attendant is present and turn off when she leaves. By running Unit 1 all the time, the room is maintained at HEPA air quality while keeping fan noise to a comfortable minimum. Filters in Units 2 and 3 need to be changed only once per year. In these 3 videos, I presented you a solution for long-term care that can achieve a theoretical improvement of 99.93% over your regional statistic. How close your actual improvement will be depends on how well you adhere to the tilt angle, to the distance of 2 to 3 meters, and to the protocol of always maintaining a crosswind between the attendant and the resident during every interaction. The real beauty of this device is that it comes into full glory immediately from the moment you turn on the power switch. It may be hard to believe that such a simple solution can be so powerful, perhaps 100 times more effective than the high-tech mRNA vaccines. But don't get me wrong, vaccines are great. However, a complex problem doesn't always need a complex solution to be a very good and of immediate use. Unlike vaccines, this solution is not negatively impacted by new variants or new pandemics. So keeping it in service, even after vaccination, provides an added assurance against the sudden appearance of other possibly worse respiratory diseases in the future, while mitigating disease and death during the time it takes for vaccines to be designed or tweaked and manufactured for any respiratory disease. In addition, this solution will also be effective against the common flu, giving seniors a much better quality of life with less stress on personnel, even after the pandemic is gone and care workers no longer need PPE. You might be thinking, can this solution be adapted for other environments, like schools, gyms, offices, restaurants, and even hospitals? Interesting question. Let's be careful. An ad hoc installation of a commercial freestanding or wall-mounted air purifier may only give marginal improvement, perhaps 1 or 2% at best. So we have to be cautious in thinking that purified air alone can truly be useful. However, the purified crosswind concept I demonstrated here, with judicious airflow engineering that directly intercepts and syncs the immediate transmission modes specific to each environment, most certainly, yes. If you have the resources and wish to do a control study to increase traction for this concept, please cite these videos and share your results with us all. You may provide a reference to your publication in the Facebook link below. If you are interested in translating, I provided a link to the script, but I ask you to please reference the original videos presented here. Reports are just coming in that we will need near 90% vaccination compliance for herd immunity against COVID-19. We are all in a war. If you work in other disciplines like me, I call on you to bring in your own new ideas and publish them ASAP, even on YouTube as I did here, and let the public evaluate the merits. Thank you for watching.